Hello, students. Had a few more out of section 4.2. And let's see here. It was question 7, 7, 11, 17. So let's take a look. I guess we'll go to part B. 7, 11. Find the greatest four-digit whole number that has exactly 3 positive factors. So we're looking for a four-digit whole number that has exactly 3 positive factors. All right. Well, we've got a pretty good idea about what takes 3 positive factors, right? Let's get a little white space in here. Let's see. All right. So let's see here, 3 positive factors. So we saw today that the numbers had 3 positive factors were 4, 9, 25, 49, which turned out to be 2 squared, 3 squared, 5 squared, 7 squared, and we came to the conclusion this would be p squared, which is any prime number. So prime number squared. We need a four-digit whole number, but we need a prime number squared as well. So we've got definitely our list of prime numbers that we have. And we know we only needed to check up to 7 to get all of those amazing prime numbers from 1 through 100. So we kind of know those. We know 7 squared is 49, so we need something quite a bit bigger than that. If it was going to be a four-digit whole number, and we want the greatest four-digit whole number, so 4 digits, the biggest four-digit number would be something like this. And so, like, if I want to find the prime number that's kind of next to this, a prime number squared, because that's what I need, that has exactly 3 positive factors. Yeah, so I'd probably just take the square root of this and see what pops up. So let me jump back. Let's take a look. We'll go up to Desmos real quick. Let's see here. Desmos is here. Oh, got my white space on the screen. Okay. Let me clear all my drawings for a moment. Graphing calculator. And what do I want? SQRT 9999. Well, not a surprise. It's right close to 99. So I need something that is close to 99. And let's see here. Yeah, it's not going to bring those back. So I need something very close to 99. So if I'm looking through there, I know right off the bat that it can't be 99, right? So I need something a little bit less than 99. So I got like 99 point something. Okay. So 99 we know is out. It's divisible by 9. We know 98 is even. So it is out. We've got 97 would be next. So again, this would be 97 squared. And that's a decent candidate, right? If I kept going like 96, this is a multiple of 3. 95 is a multiple of 5. 94 is even. 93 is a multiple of 3. 92 is even. 91 is divisible by 7. So that's kind of a nice one right there. We kind of did this one in class. So this is 70 plus 21. So notice if this is divisible by 7, then I would add 7 to get to the next one. So this number right here is not divisible by 2, by 3, by 5. We can see that. And it misses the 7s. So that means this number is a prime number. And if we square it, let's see here. So let me jump back over to the other piece with Desmos. And if I square it, let me remove all those pieces here. So if I say 97 squared is 9,409. So that would be the biggest four-digit number that has exactly 3 factors. So there you go. And again, that's why it's really helpful to have those tools for 2, 3, 5, and 7, and also that idea for square roots. So, yeah, not a bad one. I mean, you should be able to, not saying that you frequently do this, but if you were starting with a list of numbers, this makes me almost want to put one like this on the test. But to say, if I was just starting with a series of numbers, and let's just say it was 100 and, I don't know, 102, right? 103, 104, 105, 106, right? That's a 106, 107, 108, 109. If I gave you a list of numbers, right? Right? 115, 116, 117, 118, 119, 120, right? And we could keep going, but let's just say we had oops, that's a 122, 123, 124, 125. If you had a list like this and you were trying to find which of this chunk right here was prime, like I would do very similar to what we did in class, where we said, wait a minute, all the even numbers, we know they're not prime, so I'm going to use blue, and I'm just going to cross off all the even numbers. Okay. Now I'm going to use green, I guess. I'll use green to get multiples of 3. So I need something that is a multiple of 3. And so add the digits and get something. So like here, 120, right? 120, that's a multiple of 3. And so if you want to find the rest of them, then just add 3, right? So 120 is a multiple of 3. So add 3. And then subtract 3. So take away 3. 117, 114, 111, right? And what's really nice is when you do a little table like this, in this case, it turned out to be in sixes, um, everything's kind of nicely in here. I've ruled out a ton of stuff so far. Let's jump over. I'll do orange and we'll do multiples of 5 next. So multiples of 5 would be here. And then orange, it looks like more of a brown. Okay, there's a 5, right? Here's a 5. There's a 5. There's a 5. There's a 5. So again, I've ruled out a couple additional numbers. Let's see here, 5s, then 7s. So this is one where I think sometimes students are like, wow, I need to memorize all those. I'm not memorizing anything. I'm looking for a multiple of 5, and then I'm counting back by 5s from there. Or I find a multiple of 3, and then I count back or forward by 3. So I don't have these memorized. That would be a real pain. And I think most of us have better things to do with our time anyway. So let's find something that is divisible by 7. Okay, so let's just see here. 70 is divisible by 7. I need to get into this range though. So why don't I do 70 plus 49? Pick another multiple of 7, and that would be 119. Okay, got it. So 119 is divisible by 7. Then just count back 7 from there, or count forward 7. Because if I count backwards 7, I get 112. That's a multiple of 7. If I count backwards 7, maybe I'll do a weird little thing like this for the 7s. Those are 7s. These are 7s, right? And like I could take the square root here of like the highest number here should be like a 121, right? The square root of 121 turns out to be 11. Oh, which is cool, right? Because then that's not prime, that's a multiple of 11. And I could keep finding multiples of 11 by just subtracting 11. So take this and I get down to 110. That's a multiple of 11. Below that would be 100 minus 1. So 99 would be a multiple of 11. Okay, so I could keep doing that. So yeah, so this square root though tells me I only need to check up to 11. So I need to check 2, 3, 5, 7, and 11. Well, the purples are 11. The 7s are the black on the side. I checked for 7s. I checked the 5s. What was 5? Kind of this brownish orangey thing. What was 3 was kind of a green underline, and blue was a pass through. I checked 2, 3, 5, 7, and 11. Every other number in this table must be prime. Must be. So 103 is prime. 107 is prime. 113 is prime. 109 is prime. Everything else has been crossed off with at least one color shading. So that gives me 4 prime numbers in this. Okay. All right, and again, that could be for any set, right? Who knows? Maybe it was 200s or 300s. You just take the square root. It'll tell you what you have to check up to. But really, find one multiple and then add or subtract to get the other. So it could be a little bit quicker than you might think to find a group of prime numbers instead of just finding one. All right, let's take a look. So that was number 7. Let's see what else the student was looking for here. Number 7, number 11. Okay. So number 11, is it possible to find non-zero whole numbers x, y, and z? So it says non-zero. This is a big part. When you have an exponent of 0, remember that's the number 1. So when they say non-zero, it means none of these will turn into the number 1. Such that 2 to the x times 3 to the y equals 5 to the z. Well, let's go back to the fundamental theorem of arithmetic. Fundamental theorem of arithmetic says a prime factorization is unique. So if you have 2 to the x times 3 to the y, and these two exponents, x is not 0 and y is not 0, then that means you definitely have whatever this number is, whatever you want to call this number, we definitely know that, okay, thank you. Oh, well, it's not going away. We definitely have a 2 has to divide n, and 3 has to divide n, again, because the exponents are greater than 1. So if 2 and 3 divide n, what do we pick up for free? We know 6 divides n. That was from our divisibility test. But we're not asking about 6 dividing n. We're asking, it's not about the number n, except that we know n is equal to this thing, which is 5z. So the question is, for these numbers, we know 2 divides the left-hand side. We know 3 divides the left-hand side. Would you say it's true that 2 has to divide 5 to the z power? Is that true? And if that's the case, then 5 to some power has to equal the number 2 times a whole number. What would you multiply by 2 to get 5 in terms of a whole number? Well, we can try to get 5 if I plug in the number 1. 1 times 2 is 1. Or sorry, 1 times 2 is 2. Sorry about that. I'll plug in 2. 2 times 2 is 4. And 3 times 2 is 6. So there is no whole number I can plug in here, which says 2 does not divide 5 to the z. So if 2 divides on the left and it does not divide on the right, the fundamental theorem of arithmetic says if it was going to divide on one side, it has to divide on the other side if they are equal. And what that means is we can't find any numbers that are going to make this work. That is all she wrote. Okay, let's keep checking. 17 came next. Let's take a look. It says fewer than 100. He puts them in piles of 2, 3, 4, 5, or 6. He has 1 card left over each time. Okay. How many baseball cards does Jose have? Well, he has fewer than 100, so that's helpful. But if you make piles of 2, then he has to have 1 card left over, right? Now, piles of 3, that would be a little bit different. Let me get a little bit of space here. Okay, yeah, so this is not a bad problem, but again, just a little bit of kind of thinking it out before we jump in there. So I need to have something that when I divide by 2, leaves me 1 left over. So whatever my number is, how many baseball cards, I know it's 2 times something plus 1. It's also 3 times something plus 1, right? Let's see here. Because he has 1 card left over. He puts all his cards into these stacks. He has 1 card left over. So let's see here. Yeah, so if you think about kind of if he had something like, let's see here, 20 cards, 22 would go in there evenly, but I have to have 1 left over, so I must have had 21 cards. Okay. So yeah, that's a possibility. Then we try 21 though. 21 when I check with 3, that doesn't work because 3 goes in there evenly. He's supposed to have 1 card left over. So I need something that's also got 1 left over when I divide by 3. Okay. Which If you think about the 2 and the 3, the 6 is going to come along for the ride. So I need something that is actually 6 times some number plus 1 is the kind of thing I'm looking for, but it also has to be divisible by 5 with 1 card left over. Now 6 and 5 don't have anything in common, so with a 5 and a 6, that means I'm looking for a multiple of 30 that has 1 card left over. Okay, and this plus 1 is kind of coming along for the ride. And then it has to also be divisible by 4. So look at 30. 30 is 2 times 3 times 5. Does 4 go into this number? Let's see here. 4, you can write 4 as 2 squared. 2 squared does not go into that number, which means the number of cards that I have needs more. 30 is not enough. It needs another 2. So the number I need actually has to have 2 squared. It has to have a 3, and it has to have a 5. And if you multiply that out, you get 4. 4 times 5 is 20, times 3 is 60. And don't forget, we need 1 more at the end. So how many baseball cards does he have to have? He's got to have 61 cards. It doesn't have to just be 61 cards, because again, it could be some multiple thereof. So what you need to think of it as is really 60 times some number plus 1. But if you check that and start plugging in different numbers, you're not going to end up with tons, right? You're going to have 60 plus 1, which I have right there is 61. You're going to have the next group of 60, which would be 120 plus 1, which would be right here is 121. So you're not going to have a ton of these options. And because it says that Jose has fewer than 100, I kind of rule out anything that goes bigger than that. And that tells you you got to have exactly 61 cards left to make that work. Cool. Let's see here. Math connections. Okay, got a couple math connections. Number 4. Let's take a look at math connection number 4. Hold on. Let me stop sharing. Come on, computer. There we go. Okay. I don't know what was happening there. I think it's over. I hope it's over. Let's see here. Here we go. Let m equal this plus this without multiplying. Show that none of the primes less than or equal to 19 divide m. All right. Well, this is your chance to kind of use those theorems that we've been talking about. Those theorems are there to one, to make things easier for you. And so let's do that. Okay, there we go. Let me get a little bit of white space here, just so we can really focus on question number 4. Okay. So the goal is without multiplying the numbers out. And if you multiply all those numbers out and add them together, it's going to be a pretty big number. And you'd have to go through and do division for most of these pieces. But instead, why don't we use some of our theorems? Because I know if I was to look at the number m, and it's broken up into 2 times 3 times 5 times 7, you could immediately know that 2 divides this portion. So if I want to call this A, and 11 times 13 times 17 times 19, if I called this B, then I know 2 divides A, 3 divides A, 5 divides A, and 7 divides A. I also know 11 divides B, 13 divides B, 17 divides B, and of course 19 divides B. So I have these pieces here. But what's great is by just looking at it, I know 2 does divide the first number, but 2 does not divide the second number. So if 2 divides A and 2 does not divide B, what can we say about 2 dividing A plus B? Is it that it does divide or does not divide? And so here I could say, well, I know 2 does divide the first number. It does not divide the second. When I'm adding them together, that means 2 does not divide the A plus B. So there's my explanation on why I can tell you that 2 does not divide M. So, oops, I got a little crazy. Sorry about that. So 2 does not divide N. You could repeat pretty much the same argument with any one of those other numbers. And the way it's written, that number may not be prime, but that's okay. Our goal is to show that none of the primes less than or equal to 19 will divide, and that's exactly what we did. All right, let's take a look then. There's MC4, MC10. Okay. Explain why each of the following numbers is composite. Hmm. Well, I mean, maybe I'll do one of them. Think about what composite means. Composite means that it is composed, that's where it comes from, is composed of multiple primes. So it has to be multiple prime numbers multiplied together. So for example, 6 is composite, 6 is 2 times 3. Okay. Has to have more than 2 factors, has to have a product of primes, things like that. If you just had the number 3, 3 would not be a composite number, it'd be prime. So like for part A, why is this composite? Yeah, it has factors of a 3 and a 5, and you could keep going, but you really don't have to. All you need is one number that is not 1 or the number itself. So I just need one value. Okay, that's it. Yeah, for B, this is an addition problem now. So in order to be composite, we need a factor. And is there a number that divides both of those quantities? Okay. Let's see here. Well, 2 goes into this number, and over in the other part, there's definitely something that 2 goes into that part. Since they're all multiplied together, 2 must divide A, and 2 divides B. Therefore, 2 divides A plus B, and that means, yes, 2 does divide your number, which makes it composite. Okay. And so I think for the rest of that one, it's very, very similar. Yep. Okay. So that's the goal on number 10. You got to be able to show why it's composite, which means you have to show a factor that's not 1 or the number itself. And let's see here in question 12, it says, let's take a look. Question 12. I think this is the one with the ages. So yeah, I'm probably not going to give too much on this one. Yeah, I give a video of this one already, kind of showed how I kind of set that one up. So I feel like if you want to see, go. I've already put a video together for the MC portion. So I don't think I'm going to make another video on that. Yeah. So yeah, at the end of the day, you should be able to know 2 things. You should be able to know the door number, and you should be able to know the ages of the teacher's children. Yeah. And so again, I would recommend watching the video I already made on the MC, where I kind of push you in the direction of how would I kind of set this up. Definitely need 3 numbers. The product is 72, and the sum is some quantity that we may not have tons of information about. All right. I think that does it. Let me make sure. I had homework 7, 11, 17, and math connection 4, 10, and 12. All right. That does it for here. Off you go.